In this session, let us learn about primes followed by fundamental theorem of arithmetic. What is prime number or what is prime? Let us look at the definition first. An integer p greater than 1 is called prime number or simply prime if its only positive divisors are 1 and p. Okay, an integer p greater than 1 is called a prime if its only positive divisors are 1 and p. Any number greater than 1, any integer greater than 1 can be called as prime if it has got divisors itself and 1 as a divisor. An integer greater than 1, any integer greater than 1 which is not prime, is called composite number or simply composite. Okay, if I consider first 10 numbers, among first 10 integers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, among this, if I consider the numbers, the integers which has got divisors as itself and 1. Okay, this 2, its divisors are 1 and 2 only. When I consider 3, so these two are primes. If you look at 4, it has got divisors 1, 2 and 4, so it cannot be prime. When I look at 5, it has got divisors 1 and 5 only. 6 has got 3, 2 as a divisor, so 6 cannot be a prime. And 7 has got divisors 1 and 7 only. So 2, 3, 5, 7 are the primes. I hope you understood. And according to our definition, integer 1 plays a special role. Okay, it is neither prime nor composite. Okay, neither prime nor composite. So by definition, the number has to be greater than 1, integer has to be greater than 1, and its divisors are only 1 and itself. Then I can call those number as, that number as, particular integer as prime. If p is a prime, okay, and p divides ab, then either p should divide a or it should divide b. So let us look at the theorem, how it is. If p is a prime and p divides product ab, then either p divides a, or hope you can see a or p divides b. Hope you can see. Yeah. So you can check this with the example. Suppose I have a number 36, okay, an integer 36. I know prime number 3 divides 36. Okay, this 36 can be written as a product of 6 and 6, 9 into 4, or 18 into 2, or 12 into 3, like that. you can observe one thing. All these numbers in all this set, 3 divides at least one of the factors involved in this product. This 3 divides at least one of the factor in these products, right? Here of course 3 divides 6, 3 divides 9, 3 divides 18, 3 divides 12, 3 divides 1, at least one it divides, right? So you can say, if I consider this, if P divides AB, that is AB, if 3 divides 9 into 4, then of course you can observe 3 divides 9, right? In this case 3 divides 18. In this case, in fact, 3 divides 12 also, 3 divides 3 also. Okay, with the example, proving is very easy. Okay, even theoretical proof is also easy. So let us look at it. If P divides A, then we are done, right? It's given P is a prime and P divides AB. Then if P divides A, then nothing to prove. It's easy. We are done. If not, that is, if P does not divide A, means P is not a divisor of A, then what happens? By definition, their GCD is 1, in the sense P and A are relatively prime, right? Now, by the theorem, we can write there exist integers x and y such that px plus ay equal to 1, right? For some integer x and y. Now what I do is I'll multiply this equation by b, okay, so that it will be pbx plus aby equal to b. Since p divides pbx, P divides P, so P divides PBX, and since P divides AB, P also divides ABY. It is because P divides AB, it's already mentioned. So P divides PBX and P divides ABY. So it should divide addition of these two terms, right? So P also divides PBX plus ABY. Right? What is PBX plus ABY? It's nothing but B. Hence the proof. That is, what if P does not divide A, then they have to be relatively prime to each other. So by definition, by theorem, I can write it Px plus Ay equal to 1 for some integer x and y. So I'm multiplying by B to this equation. And since P divides P, I can write P divides PBX, okay, and since P divides AB, P also divides ABY. So from these two, P divides PBX plus ABY, so P divides B, hence the proof. See, now this theorem is extended to products of more than 2 terms. Okay, now I have taken only 2 terms, A and B, P dividing A, B, product A, B, so that either P should divide A or P should divide B. Now, I'm just extending it to product of more terms, okay. That is, if P is a prime and P divides the product of numbers integers a1, a2, dash dash, an, and P divides ak for some k, okay, for some k, where k lies between 1 and n. This is first corollary, and the second corollary says if p, q1, q2 dash dash qn are all primes and p divides the product of q1, q2, qn, then this prime number p is equal to some qk. For some k where k lies 1 less than or equal to k less than or equal to n. These are the two important results. We should keep it in mind. See, when I consider two terms, there is no problem. We have proved P divides AB implies P divides A or P divides B. And the same thing if I have more terms, okay? Product of more terms. If P divides this product, then P also divides some, P also divides some AK for some K. And if P, Q1, Q2, Qn are all primes, then if P divides product of these terms, then P equal to sum of any one, P is equal to any one of these prime numbers. Say P equal to Qk for some K. Now let us look at one important theorem, that is fundamental theorem of arithmetic, which is also called as unique factorization theorem. Unique factorization theorem says every positive integer n greater than 1 can be expressed as product of primes, and this representation is unique apart from the order in which the factors occur. Okay. See, if that integer which we are considering, if it is prime, then no problem. Of course, it can be written as a product of two primes. So no problem if an integer is prime. What happens if it is composite? Okay, it's not mentioned. It's just mentioned every positive integer. Okay, so n can be prime if it can be prime, or it can be composite. Right? If it is prime, then nothing to prove. Because if it's prime, then of course n can be written as 1 into n, and this representation is unique, no issue. If it is composite, if n is composite, then there exists an integer, say d, satisfying the condition satisfying the condition that this d divides n and d is less than n. Of course, it is greater than 1. Okay, if it's a composite number, then it has got a divisors, right? Let me take one such divisor, that is d, and it is less than n. Now, in fact, it is n has got set of divisors. Okay, by well ordering principle, say among all such divisors of n, all such integer d, let me choose one such integer, say p1, which is the smallest one. See, it has got set of divisors. Okay, among all such integers d, choose one such integer which is the smallest one. Okay, among all such integer d, choose say p1, choose integer p1 to be the smallest. Okay, then P1 must be a prime number because see, what happens is, if it is not prime, this is the reason I'm giving. If P1 is not a prime, then what should be true? It should have some divisor, say Q1. Okay, if it's not a prime, then it has a divisor, say Q. Okay, if it's not a prime, then it should have a divisor Q in such a way that 1 less than Q less than P1. Right. Then, since it is a divisor, this Q should divide P1. Q divides P1, and also I know P1 divides N. It just implies that Q divides N, which contradicts the fact that P1 is the smallest divisor of N. P1 is the smallest divisor of N. Okay. Which contradicts the choice of P1 as the smallest divisor of N. Of course, it's not equal to 1. Therefore, what is to be true? P1 must be prime. Okay, I hope it's clear. It has to be prime. If it's not a prime, then it must have a divisor. So let me take a divisor as Q. Okay, a divisor Q divides P1. We already have taken P1 as a divisor of N. So Q divides P1 and P1 divides N. Therefore, Q divides N. When Q divides N, it contradicts the fact of choosing P1 as a smallest divisor of N. Okay, so P1 must be prime. Therefore, we can write N as P1 into N1, where P1 is prime and N1 is less than N. Some times of P1 gives me N, that sometime I'm denoting it as N1. So now I have got N as product of two numbers, among them one is prime. If N1 is also prime, then no problem, no issue. But if N1 is not a prime, then I have to repeat the same steps again. Okay, if N1 is prime, then we have N equal to P1 N1, that is product of primes, right? So no problem. If N1 is not a prime, means if it's a composite number, then we have to repeat the arguments to produce a second prime number, say P2, in such a way that N1 is equal to P2 into N2. Okay, this I'm considering. If it's composite, then I'm taking it as a product of two numbers, P2 N2, and so that N will become P1 N1, P1 N1 is P2 N2, right? With 1 less than N2 less than N. If N2 is prime, then no need to go further. Otherwise, if N2 is prime, then no need to go further. Otherwise, write n as P3 N3 with P3 as prime. P3 is prime. Okay, this P3, sorry, N2 I am writing it as N2. If N2 is prime, no problem. If N2 is composite, then I am writing it as P3 N3, where P3 is prime, and this P3 into N3 I am writing with P3 as prime. P3 I can write it as P3, I'll keep it as it is. N3 I'm writing N I'm writing in fact. N can be written as P1 P2. In place of N2 I can write P3 N3 with 1 less than N3 less than N2, less than N1 in fact. Okay, so this decreasing sequence goes on like N is greater than N1, greater than N2, like that, greater than 1. After finite number of steps, say after nk minus 1, you are stopping because you are getting that nk minus 1 as a prime. Okay, if you go on decreasing, you will end up at after some times you will end up getting n as a prime number itself. Okay, the decreasing sequence. Thus, after finite number of steps, I'll just write it down. After finite number of steps, say nk minus 1 is a prime number. You are getting nk minus 1 as a prime number, and I'll call it as, say, pk. Therefore, it leads to the factorization of n as p1 into p2 into p3 dash 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 k minus 1th step. You are getting a prime number itself, and I'm calling it as pk. So n is written in terms of product of primes. Now I have to check for the uniqueness. Okay, let us see. Let us say n has got two representation. One is product of primes p1 p2 dash dash pk, and another is again a set product of primes q1 q2 dash dash qk. Okay, I'll just write it down. So two representations, p1 into p2 into p3 into pr, q1 into q2 into dash 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 qs with r less than or equal to s. Here pi's and qj's are primes, and they are written in increasing magnitude. It means p1 is less than or equal to p2, less than or equal to p3, like that, less than or equal to pr, and similarly q1 less than or equal to q2 dash dash less than or equal to qs. So it's mentioned p1 divides n, product of primes. When I consider if now prime divides, I'm sorry, because p1 divides n, this p1 divides n can be written as p1 into p2 into dash dash p2 dash dash pr. Then p1 divides this also. If I use this representation, right, I can also say p1 divides product of other representation q1 q2 dash dash qs, right? And I can also say p1 equal to qk for some k. For some k, I can say p1 equal to qk. But if that is the case, then p1 is greater than or equal to q1 right? See, this P1 is dividing the product this, and since this is also prime and these are also prime numbers, by the corollary we have seen this P1 is equal to any one of this prime number, right? So for some k, P1 is equal to Qk. Then either they are equal or P1 is greater than or equal to Q1. Similarly, I can say Q1 divides n, and n is nothing but I am taking the other representation as a product of P1, P2 dash 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 PR. Okay, so this Q1 is equal to some prime number pk for some integer k, right? Some k. But then by the corollary, the second corollary we have observed, we mentioned it, if P1 if P, Q1, Q2 dash Qn are all primes, P divides the product Q1, Q2, Qn, then P equal to Qk for some k. So same thing I have applied here. If that is the case, then Q1 is greater than or equal to P1, right? So from these two if you observe, then P1 equal to Q1, okay? If I use this P1 equal to Qn, then I have got representation n as P1, P2 dash dash PR and Q1, Q2 dash dash Qs. If P1 equal to Q1, then I can cancel those two terms, right? The remaining is P2 into P3 into dash dash PR equal to Q2, Q3 dash 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 Qs. Now repeat the same process to get P2 equal to Q2, P2 equal to Q2, and in turn you get, you can cancel P2, Q2, and you are getting P3, P4 dash dash PR equal to Q3, Q4 dash dash Qs. Continuing like this, if the inequality R is less than S, okay, we are continuing like this. If this R is less than S, we would eventually arrive at the situation where this part gives me 1, and here there are few more terms, say QR plus 1, QR plus 2 dash dash Qs. If R is less than S, I am getting this after some number of steps, okay? In fact, this is not at all possible to have like this. Product of the integers giving me the value 1. In fact, product of primes, I am getting the value total product as 1, which is not at all possible, because it's mentioned each Qj is a prime and it is greater than 1, so this is not possible. I cannot get the product of primes as 1. So what is true? This R should not be less than yes, R should be equal to yes. Hence R equal to yes. So which just implies P1 equal to Q1, P2 equal to Q2 dash dash dash, PR equal to QR, R equal to yes, so it's okay. So what does it imply? This representation L as P1, P2 dash dash PR and Q1, Q2, Qs, these two representation are identical. So I can just write 2 factorization are identical. 2 factorizations are identical. Remember one thing, this factorization is unique, but the prime numbers which are appearing in the representation, say in this case, suppose I'm writing it like this, no? In this, P1 may be equal to P3. Any one prime number, say P1 or P2, may occur more than once. Okay, but the representation is unique. If I write it in one form, then I cannot write it in any other form. The numbers may repeat, but the representation won't. I'll just explain with an example. Suppose that number which I have considered, that is 36. Okay, this 36, I'm writing it as, say, 18 into 2. Then this 18, I can write it as 9 into 2 into 2. And this 9 again, I'm writing it as 3 into 3, 2 into 2. In fact, I have to write always in increasing order. You got? This representation is unique. Just the thing is, numbers are repeating. Okay, it's okay. No problem if it is repeated. But I cannot write it in any other form, like any other form in the sense, any other way of product of primes. Okay, so this representation is unique.